is to demystify the mess that makes machine learning algorithm work so you can have a stronger foundation for your machine learning journey. This week, we're focusing on the essentials: numbers, functions, and of course, graphs. These concepts are fundamental building blocks that will help us understand how machine learning models work. But before we start, I'd like to mention that it's a friendly and inclusive space. Let's encourage each other and lift one another up. Negative comments, jokes, or behaviors that put others down have no place here. Please maintain a professional and friendly attitude. Our events are focused on learning and sharing knowledge. If something doesn't feel right, let the host know during the event or reach out via email. We are here to make sure everyone feels comfortable and, of course, included. This event series will be recorded. So, let's start. Machine learning isn't just about coding and applying pre-built models. A true understanding of machine learning requires a solid grasp of the underlying mathematical principles. Math is the language of machine learning. It's how we express the algorithm, analyze the behavior, and understand the strengths and limitations. By strengthening your mathematical foundation, you'll be able to understand how algorithm works. You'll be beyond just using the tools and truly understand what's happened under the hood. Develop intuition. You'll gain a deeper intuition for why certain algorithms work and when they are most appropriate. Debug and troubleshooting. You'll be better equipped to identify and fix problems or models don't perform as expected. And of course, innovate and create. With a strong math foundation, you'll be better positioned to develop new algorithms and, of course, new techniques. This week, we're focusing on some fundamental math concepts that are essential for machine learning. We're calling it a math refresher because these are likely concepts you have encountered before, but we'll revisit them with a focus on how they apply to machine learning. Specifically, we'll be covering linear equations and their solutions. Linear equations are the building blocks of many machine learning models. Understanding how to solve them is crucial for understanding how these models learn. Functions and their importance. Functions are at the heart of learning. They describe the relationship between variables and are used to represent models themselves. Plotting graphs to visualize relationships. Visualizing data and functions throughout graphs is, of course, essential for gaining insights and understanding the behavior of models. These concepts might seem basic, but they are absolutely crucial. They form the backbone of many more advanced mathematical techniques that we'll explore in future sessions. A solid understanding of these fundamentals will make it much easier to grasp the more complex material later on. So, get ready to refresh your math skills and see how they connect to the exciting world of machine learning. We will be diving into linear equations next. So, let's starting our math refresher with linear equations because They are fundamental building blocks, as I mentioned before, in machine learning. Many machine learning algorithms rely on linear relationship between variables. Think of it this way: many real-world phenomena exhibit at least approximately a linear relationship. For example, the size of house often has a really linear relationship with its price. Understanding linear equations allows us to model these relationships mathematically. These equations help us represent how different factors of features influence the outcome we are trying to predict is our target variable. Mastering them unlocks a deeper understanding on how many machine learning models work at their core. It's like learning the alphabet before trying to write a novel. It's an essential first step. A linear equation is an equation that can be written in the form y equals mx plus b. Let's break down what each of these letters represents, because understanding them is key to understanding how linear equations work and how they are used. Y, one of our variables, is represents the dependent variable, the thing we are trying to predict. Think of it as the outcome. In our sea level example, y represents the mean sea level. Its value depends on the value of x. X, this is the other variable. It's an independent variable. A factor that influences y is the input. We can choose, for example, in next steps, we will see example with C and years, and it's the input, and in our example, X represents the year. We can choose different years, X values, to see how the C level Y values changes. And this is the slope. It tells us how much y changes for every unit change in x. It's the rate of change. A steep slope means a big change in y for a small change in x. A shadow slope means a smaller change in y for the same change in x. B. This is the x-intercept. It's the value when x is 0. It's where the line crosses the x-axis on the graphs. In our example, you'll see later the y-intercept would represent the sea level in the year 0, which is a bit theoretical in this case. Understanding these components, y, x, m, and b, is crucial because they allow us to translate real-world relationships into mathematical equations and then use those equations to make predictions and draw conclusions. The key characteristic of linear equations is that its graph is a straight line. This straight line visually represents all the possible x, y pairs that satisfy the equations. Every point on that line is a solution to the equations. Solving a linear equations means finding the values of the variables that make the equation true. In simpler terms, we are looking for the specific values of x that make both sides of the equations equal. It's like finding the missing piece of puzzle that makes everything fit. Think of it like a balance scale. Our equation is like the scale, and we want to find the x value that perfectly balances both sides. If we find the correct x and substitute in the original equation, the left side will be equal to the right side of the equation. For similar linear equations with one variable, usually x, we can use algebraic manipulation to isolate the variable. This involves performing the same operations on both sides of the equations to gradually get x by itself. We might add or subtract the same number from both sides, or multiply or divide both sides by the same non-zero numbers. The goal is to keep the equation balanced while we move terms around until we have x some value. That some value is our solution. For systems of linear equations with multiple variables like x and y, we have multiple equations that all need to be true simultaneously. And we can use techniques like substitution or elimination to solve these systems. Substitution involves solving one equation for one variable and then substituting that expression into the other equation. Elimination involves adding or subtracting multiple of the equations to eliminate one of the variables. Understanding how to solve linear equations, both simple ones and system of equations, is absolutely crucial because many machine learning algorithms involve finding the solutions to systems of linear equations. For example, linear regression, a fundamental algorithm, involves finding the best fit line to a set of data points. This process involves solving a system of equations to determine the slope and y-intercept of that line. So, mastering linear equations is a key step toward understanding how these powerful algorithms work. We are starting our math refresher with linear equations, which are, of course, fundamental building blocks in learning, and I mentioned before about this, and many machine learning algorithms rely on linear relationship between variables. So, understanding how these equations work is essential. For example, let's solve a simple linear equation to x plus 3 equals 7. Remember, solving for x means finding the value of x that makes this equation true, that balances both sides of the equation. Our goal is to isolate x on one side of the equation. We do this by performing the same operations on both sides, keeping the equation balanced. First, we subtract 3 from both sides. Next, we divide both sides by 2. So, x equal 2 is the solution. Since both sides are equal, our solution is correct. This simple example illustrates the basic principles of solving linear equations using algebraic manipulation to isolate the variable and find its value. These principles are essential for understanding how to solve more complex equations that arise in machine learning. Linear equations are used in many different ways in machine learning. They are not just abstract mathematical concepts, they are the workhorses behind some powerful algorithm. Let me give you a few key examples. Linear regression. This is a fundamental algorithm for predicting a continuous value like house price based on linear relationship between the input features. Imagine you want to predict house price based on their size. You might find that there's a really linear relationship. Bigger houses tend to be more expensive. Linear regression issues a linear equation to model this relationship. Perceptron. This is a simple neural network model used for binary classification, deciding where something belongs to one category or another, like spam or not spam. The perceptron uses a linear equation to create a decision boundary. It takes the input features, like the number of certain keywords in an email, for example, and combines them linearly. If the result is above a certain threshold, the email is classified as spam. Otherwise, it's not. Support vector machines. They are used to find the optimal hyperplane that separates data points into different classes. While support vector machines can handle complex, non-linear boundaries using kernel tricks, the underlying principle still involves linear equations. The support vector machines algorithm tries to find the best linear equation or hyperplane in higher dimensions to separate the data points as clearly as possible. Understanding the linear equations, of course, the foundation for understanding this and other more complex machine learning models. There are the basic building blocks upon which many more sophisticated algorithms are built. So, by mastering linear equations, you are not just learning about straight lines, you are gaining the key to unlock a deeper understanding of how machine learning works. Linear equations are used in many machine learning algorithms. I mentioned about this. In linear regression, we might predict, for example, house price based on size using an equation like uh, y equal 1000x plus 50,000. Here y represents the predicted house price and x represents the size of the house. The 1000 represents the increase in price per until of size and 50,000 is the base price. This equation allows us to model the relationship between size and price and make predictions for new houses. In a perceptron, we could classify emails as spam based on a linear combination of word counts. Imagine we have feature representing the count of certain words. The perceptron combines these counts in a linear way to determine if an email is likely to be spam. Even simple feature scaling can involve linear equations, like converting Celsius to Fahrenheit. This conversion uses a linear equation to transform the temperature from one scale to another. So, linear equations are used in various ways, from building predictive models to processing data. Mastering linear equations is absolutely essential for any serious about understanding machine learning. It's not just a nice to know piece of math, it's a foundational concept that will build upon extensively in future sessions. Think of it as the grammar of the language of machine learning. You need to understand it to speak fluently. We'll be using linear equations and the concept behind them again and again as we delve into more complex algorithms and models. Next, we'll explore another crucial mathematical concept: functions. Functions are closely related to linear equations, but they are even more general and powerful. They allow us to model a wider range of relationships, and they are at the very heart of how machine learning models learn and make predictions. So, understanding functions is the next key step in our journey to demystify the math behind machine learning. I'm excited to explore functions with you and show you how they bring even greater power and flexibility to our machine learning toolkit. Let's talk about functions. So, f of functions is at its core a rule. It's a rule that takes something as an input and produce something else as an output. But it's a very specific kind of rule. It assigns each input to exactly one output. You can put the same input into a function and sometimes get one result and sometimes get a different result. It's a consistent and predictable. We use a special notation to represent functions. This is read as f of x. The x inside the parentheses represents the input, the thing we give to the function. The f of x represents the output, the result we get after applying the function's rule to the output, to the input. Think of it like a machine. You put something in the input x. The machine processes it according to its internal workings, the function's rule f, and it splits something out, the output f of x. For example, imagine a function that doubles any number you give it. If you input 3, the output would be 6. If you put 10, the output would be 20. The function consistently doubles whatever input it receives. This idea of a consistent input-output relationship is absolutely fundamental to how we use functions in machine learning because at the end of the day, machine learning models are essentially functions. They take input data and produce predictions as output. A function is a rule, a very specific kind of rule. Its main concept which we need to understand. And now this vending machine analogy isn't perfect. Mathematical functions can be much more complex than a vending machine, but the core idea is the same. Input goes in, a process happened, and a specific output comes out. This consistent, predictable relationship between inputs and outputs is what makes functions so valuable in mathematics and, as we'll see, in machine learning. Let's look at some specific functions. We have a linear function and a square function shown here on the slide. Notice how each function has a distinct rule for transforming inputs into outputs. This difference in rules is what leads to the different shapes of the graphs we see. Take the Key here is that every function has its own unique rule. It's like own special way of mapping inputs to outputs. And this rule directly dedicates the shape of the function's graph. By looking at the graph, we can get a visual understanding of how the function behaves, how it transforms the input we give it. Functions are absolutely essential in machine learning. They are not just abstract mathematical concepts, they are the workhorses behind how machine learning models learn and make predictions. Let's explore some of the key roles. Machine learning models themselves are functions. At its core, a machine learning model is a function. It takes inputs, which we call features, and produces outputs, which are the model's predictions. For example, a model that predicts house price might take feature like the size of the house, the number of bedrooms, and the location as input. The model then uses a complex function to process these inputs and output predicted price. This function is what the model learns during the training process. When we also activation functions introduce non-linearly. Neural networks, a powerful type of machine learning model, are built from layers of interconnected nodes. Each node applies a function to its inputs, and these functions are called activation functions. A crucial role of activation functions is to introduce non-linearity. If we only used linear functions in a neural network, the whole network would essentially behave like a single linear function, limiting its ability to learn complex patterns. Activation functions like Sigmund or ReLU introduce curves and bends into the model's calculations, allowing it to learn much more intricate relationship in the data. This non-linearly is what enables neural networks to solve challenging problems like image recognition or natural language processing. Also, during the training process, we need a way to measure how well our model is doing. This is where loss functions come in. A loss function takes the model's predictions and compares them to the actual true value. It then outputs a number that represents how wrong the predictions are. The higher the loss, the worse the model's performance. Our goal is to minimize this loss. Think of it like a game. The loss function is the score, and we want to get the lowest score. The process optimizing is how we find the best parameters for our model. Best usually means the parameters that minimize the loss functions. We use mathematical algorithms to adjust the model's parameters, trying to find the sweet spot where the loss is lowest. This often involves finding the minimum or sometimes the maximum of a complex function. Think of it like tuning an instrument. You adjust the knobs until it sounds just right. Optimization algorithms do something similar with the model's parameters. In summary, functions are absolutely fundamental to machine learning. They represent the models themselves, introduce crucial non-linearly didn't exist. Let's be more concrete by looking at some specific example of how functions are used in machine learning. Linear regression. In linear regression, We use a linear function to model the relationship between input features and a continuous output variable. A common example is predicting house price. Our model might be y equals wx plus b, where x is the size of house, y is the predicted price, w is the weight, and b is the base price. The equation is the linear function, and the linear regression algorithm learns the best values for w and b to make accurate predictions. Logistic regression is used for classification problems, like predicting where a customer will click on advertising. Here we want to predict a probability, the probability of a click. We use the sigmod function for this. The sigmod function takes a linear combination of input features like age, location, browsing history, and squashes it into a probability between 0 and 1. So, the sigmoid function is the core function used in logistic regression to map features to probabilities. A neural network are composed of layers of interconnected nodes, and each node applies an activation function to its input. A rectified linear unit is a popular activation function. It's defined as f of x equal max of 0x. This means if the input x is negative, the output is 0. If x is positive, the output is simplified x. So, rectified linear unit function introduces a non-linearity that is crucial for neural networks to learn complex patterns. Without these non-linear activation functions, neural network wouldn't be much less powerful. As you can see from this example, functions are absolutely essential in machine learning. They're not just abstract mathematical concepts, they are the building blocks of our models. They represent the models themselves. They introduce non-linearity, which is essential for learning complex patterns. They are used to measure how well our models are doing, and they are at the heart of optimization process that finds the best model parameters. Understanding functions is therefore fundamental to understanding machine learning. Let's talk about graphs. Why is visualizing data so important? Because it helps us see things that are hard, if not impossible, to see in raw numbers. Imagine staring at a huge spreadsheet of numbers representing sea level measurement over decades. It would be incredibly difficult to discern any meaningful patterns or trends. But when we plot the data on a graph, the story it tells becomes instantly clear. Graphs allow us to quickly identify patterns and trends, like a correlation between two variables or a trend over time. Uh, Now let's look at a specific example, a scatter plot of sea level rise. There are many types of graphs, each designed to highlight different aspects of data. Totally, we'll focus on scatter plot, which are particularly used for exploring the relationship between two numerical variables. A scatter plot let us see if there's a correlation, a pattern, or any interesting trend in two sets of numbers. Our example uses real-world data, sea level measured in millimeters versus time measured in years, point to the graph. This demonstrates how we can use scatter plots to analyze real-world data and potentially make predictions, which is a core task in machine learning. By understanding the relationship between time and scene level in the past, we might be able to build a model that predicts future sea levels. That's the power of data visualization combined with machine learning techniques. Understanding how to interpret these points is absolutely key to understanding the data. Each point tells a level at a specific moment in time. By looking at the collection of these points, we can begin to see larger trends and patterns emerging. So, great job, everyone. Let's quickly summarize what we covered in this session. We started by exploring linear equations. These equations describe straight lines and can be written in the form y equals mx plus b. Remember, m is the slope and b is the y-intercept. Then we learned about functions. Functions like results that take an input and give you exactly one output. We often write this as f of x, where x is the input and f of x is the output. Finally, we saw how to represent this conceptually. We talked about different types of graphs and how graphing is essential for understanding the relationship in data. We even looked at a real-world example of sea level rise to see how this concept applies and how visualizing data can reveal important trends and patterns. We saw how a scatter plot can help us understand the relationship between time and sea level, and how we can use this information to potentially make predictions. For your homework this week, I want you to solidify your understanding of linear equations and graph. Your primary resource for this will be, of course, Khan Academy. Specifically, I want you to head over to Khan Academy's Intro to Algebra section and work throughout the material of linear equations and graph. The direct link, of course, I'll share with you later. I will also include links to other helpful resources, and I'll share in our Discord channel. So, one more thing before we wrap up, I want to make sure everyone is clear on how we'll be running these sessions going towards. So, see you next week. And this session was recorded, so later I'll share it on our GDG Ahlen YouTube channel and share this link on our Discord channel. If you have any questions, feel free to contact me directly or in our Discord channel. Once again, thank you for joining. We look forward to seeing you in our next session next Sunday. Until then, keep learning, experimenting, and building with AI.